Okay, we're going to keep on rolling here. So we're going to talk about solutions, which is where most chemistry happens. Most chemistry doesn't happen in the pure solid state or anything like that. You actually have solutions in water. So, like example, in your body, everything in your body is basically taking place in water, in a solution. We're going to talk about that a little bit here. First off, what is a solution when I say that term? That's basically, it's a homogeneous mixture. I mentioned that way back when, like chapter 1 or 2. And a homogeneous mixture, remember, homo, the prefix means like same or uniform. So a homogeneous mixture is something that is uniform throughout. And remember, we said the way to tell a homogeneous mixture was actually visually. You could actually just look at it, and it just looked the same. There weren't any chunks or floaties or anything different in it. It just looked the same top to bottom. So in a solution, though, we have two components. There's a component called the solvent, and that's the one present in the larger amounts. So in most things in water is your solvent. And then everything that's being dissolved and mixed up in the solvent, those are called solutes. So if I take salt and dissolve it into water, salt is the solute, water is the solvent. If I take sugar or coffee or whatever I put into water, sugar or coffee is the solute, and the one present in the larger amounts of the water, so it's the solvent. So solute versus solvent. But solutions though technically don't have to be just aqueous. You can have a gas solution, just a mixture of different gases. You can so even air is a solution technically. Air is a homogeneous mixture of nitrogen, oxygen, carbon dioxide, things like that. You can even have solids that are solutions. Things like bronze and brass are actually multiple metals mixed uniformly throughout. But normally, though, for us, the most common solution is going to be an aqueous solution, where water is the solvent and everything else is being dissolved in the water, whether it's, like I said, it's sugars or proteins or blood cells or whatever it is being dissolved up in there. Okay? So solutes and solvents. So, let's say you have something and it needs to dissolve into water. So let's just say, for example, it's an easy one like sodium chloride, salt, just regular table salt. So table salt is sodium chloride. It's a sodium ion and a chloride ion. So when you put salt into water, several things have to happen for that salt to be able to dissolve. So when it first goes in there, you just have a giant brick of salt in the water. But over time, what happens? Well, three things happen. First off, then, is the salt ions have to break apart. The sodium and the chlorides break apart. So that's called the solute interactions. The interactions that was holding the salt together, you have to overcome that and spread it apart. Then the water is also being held together with hydrogen bonding and stuff. So the water has to spread out to make room for the salt to mix in it. So that's the solvent-solvent interactions. Then you're going to put it all back together and put the salt surrounded by waters now. So that's the solvent-solute interactions. So we have several things. So for example, say I have what was that? Try that again. Let's say I have a beaker and I have some water in here. Okay. And I throw in a big brick of some salt. So let's say this is my salt down here. Okay, well, in order for my salt to actually dissolve and become a mixture of salt and water, I have to do all those things. So my end result is to make salt water, right? So I want to have at the end, I want to have salt and water all mixed together, if you think about this. So I'm going to have little sodiums and chlorides kind of all mixed in here together when I get done. So for that to happen, three things got to happen. I have to break apart the solute. I have to make room, break apart the water. Then I have to recombine the salt and the solute. So I have to break apart solute attractions, whatever those are, hydrogen bonding, ionic bonds, whatever. Break apart the solvent, whatever those are, hydrogen bonds, dispersion, dipole. and then put them back together and make new. Maybe it's new hydrogen bonding or whatever it is. So I have to break apart two attractions and then make a brand new one. So that's how things are going to dissolve. So then when you're all done, you're going to have that ion. It's going to be surrounded by a whole bunch of water. So now you have your new solute solvent attractions. So for example, like with water, we know water is polar, which means it has one end that's a little bit slightly positive, one end's a little bit slightly negative. So you can imagine, since water has one side that's positive and one side that's negative, what's going to happen? Well, the positive ends of the water are all going to be pointing towards, let's say, the negative ions, making positive-negative attractions. And then the negative ends of the waters will be pointing towards the positive ions, making positive-negative attractions too. So that's the nice thing about like water, is you have a little bit of both opportunities, positives and negatives. So first we break apart these, and then we recombine them with the solvent. So we're making solvent-solute attractions. Okay, so there is a very handy rule called like dissolves like that helps you predict, will one substance dissolve or mix with another one? It's just something like dissolves like. If they are alike in their intermolecular forces, then they are going to dissolve. So, for example, if they are both polar, let's say your solvent is polar and your solute is polar, they're going to mix and be soluble. If they're both non-polar, well, now they're alike, so they're going to mix and be soluble. But let's say one is polar and one is non-polar, now they're not alike, so they're not going to be soluble. So for example, oil and water. Oil is non-polar. So oil, for example, is a bunch of carbons and hydrogens. And I showed you before that if it's just carbons and hydrogens, those are completely non-polar because they have a very small difference in electronegativity. But water is superpolar. So you take non-polar oil, polar water, they're not going to mix because they are not alike. But if, let's say, you take alcohol, ethanol, that's polar. Water, that's polar. You can mix alcohol and water all day long because they are alike. So like dissolves like. Or let's say you take, I don't know, gasoline and oil. Those will mix because those are both non-polar. Like dissolves like. Okay? So that is just kind of like a qualitative rule. If they have similar forces, both polar, both non-polar, then they're going to dissolve. But we also have some what are called solubility rules that we'll see here in a second that will also kind of help us to make predictions of the solubility as a kind of a bigger picture here. So, for example, here's another one. Sugar. If you draw out sugar, it's superpolar. It's got lots of oxygens and hydrogens. It's got hydrogen bonds going on. So since that's polar, sugar dissolves in water because water is polar. Okay, so they dissolve. But let's say you try to put fat or lard or vegetable oil, right, into water. It doesn't mix because one is nonpolar, one is polar, right? Okay, so I just went through that. So, okay, polar dissolves polar, nonpolar dissolves nonpolar, but they do not mix. Okay. Okay, so when you do put something into water or solvent, and it does dissolve, it can do one of three things when it dissolves. So we're going to discuss what's called electrolytes. And you always hear that term like with Gatorade and stuff, right? You know, it's full of electrolytes, or you're going to replenish your electrolytes. It's kind of a bogus term. I always kind of have to laugh. Basically then, an electrolyte is just something in solution that can conduct electricity. So anything that is charged, it's ions in water, that is technically an electrolyte. So a strong electrolyte is something then you put into water, and 100% of it breaks apart into ions. So you put it in, all of it breaks apart. None of it stays together as a chunk. All of it dissolves. It's 100% soluble, and it makes charged particles, ions. So that is called strong because all of it does it, and it's an electrolyte because you're making things that can conduct electricity. So in order for a solution to be able to conduct electricity, you got to have things that can carry charges. So you have to have ions. So that's a strong electrolyte. Weak electrolytes are similar, but those you put them into water, and maybe only 1 in 100 of them will actually break apart and dissociate into ions. Or maybe 5 in 100 dissociate into ions. Most of it stays together as a chunk. So it is still making some charged particles, which can carry electrical current through your water, but it's not 100%. That's 5% of the solid actually dissolves into ions, or 2% or something. And then the last one will just be a non-electrolyte. So that's still soluble. It still dissolves, but it doesn't dissolve into ions. So the ones that won't make ions are the molecular compounds, because molecular compounds are made up of nonmetals, molecules. So ionic compounds can make ions. Molecular compounds, of course, can't make ions. So that'll be, sugar, carbon dioxide, things that are molecular compounds, 2 or more nonmetals. So 3 possibilities. Ionic compounds that are 100% soluble, ionic compounds that are less than 100% soluble, molecular compounds that are soluble. So these 2 are going to be ionic compounds. This is going to be molecular compounds. So you see a little picture here. So if you take some salt and put it into water, try to conduct electricity through it. Of course, a strong electrolyte, all ions, so you get a great current. You get a nice big light bulb. I'll show you this in lab this week. I think it's this week. A weak electrolyte, you put it in. A few of them break apart, but a lot of them stay together. See that? A lot of them stay together. So you get a few ions, so you get a little bit of current going. And then like sugar, well, sugar is a molecular compound, so it can't make ions. So it dissolves, but there's no ions there present for you to have electricity, so nothing happens. No current possible. Okay, so one more time. Strong electrolyte, what's it mean? 100% breaks up. So these are the ones that when you write it in a solution, you're going to put parenthesis AQ. Remember that? That means aqueous. So that's going to be these strong electrolytes, something that has dissolved 100% into water. So if it's dissolved, we say it's aqueous. Okay. So salt goes into water. So you just say, oh, aqueous. Okay, so let's look at a few of the different ones here. Now, a weak electrolyte, something you put into water, and it's less than 100%. Maybe it's 5% of it actually creates ions. Okay? It'll still be an aqueous solution. Maybe it's still dissolved, but it's not dissociating into ions. Okay? So like HF is the one I mentioned, right? So HF, you do get some ions out, but it's like 5% of them actually ionized. Well, so 1 in every 20 of these breaks apart. 19 stay together, 1 of them breaks apart for every 20. So you get a few ions, but not like the other ones where it's all 20 for 20 break apart. You get a lot of ions. Yeah?
Can you go back to the previous slide?
Sure.
Please.
What do you need?
Strong.
Yeah, so those dissociate 100%. Weak electrolytes, like I said, maybe it's 5% or less typically. Okay, and then non-electrolytes dissolve, but they can't make ions because they're not ionic compounds. So only ionic compounds can make ions. So there's going to be molecular compounds. And again, those are the ones that have 2 nonmetals, right? Okay. So there you go. Sucrose. That's 3 nonmetals. That's a molecular compound, so it can't make ions. Even though it does dissolve, which it doesn't dissolve into ions. So it's not an electrolyte. It's a non-electrolyte. Okay. Well, what was this? Yeah, I got that. Okay. Now, one thing, though, that we're all kinds of interested, especially like in medicine and in healthcare fields, is what's called then the equivalence, which is not quite the same as the number of ions. It's actually the number of charges on the ion. So if an ion is 1 plus or 1 negative, well, then the number of charges is the same as the number of ions. But let's say it's 2 plus. Well, now you're getting out twice the charge for 1 ion. Or if it's 3 plus, now you're getting out 3 times the charge for the same ion. So that is called then the equivalence. So, for example, 1 mole of sodium plus is the same as 1 equivalent. Because, again, every mole gives 1 charge. 1 mole of chloride, 1 negative, is the same as 1 equivalent. Because they each have a mole of charge. So let's say I have Let's say it was calcium 2 plus. Oh, well, 1 mole of calcium 2 plus, 1 mole calcium 2 plus gives me 2 equivalents of charge because that's 2 plus. So, or let's say it was aluminum 3 plus. Oh, well, 1 aluminum is going to give me 3 equivalents of charge out, 3 pluses out. Okay, things like that. So just whatever that charge is, just multiply it by that charge, and that's how many equivalents you're going to get out. So this is important. I'll show you on the next couple slides here, because again, in your body, you're oftentimes concerned with, okay, well, when the ions in my bloodstream are trying to react and stuff, well, they have to react based on their charges, right? So 2 positives need 2 negatives, 3 positives need 3 negatives. So I have something in there, let's say that it is naturally 3 positive, well, then it's basically 3 times as effective in some cases, something that's only 1 positive. Or 2 pluses, maybe it's twice as effective at reaching out to negatives, something that's only 1 negative. So the charges become important in this. So that's table 8.5. If you want to make a little note there, come back to that. So if you ever look at like a blood test, sometimes you get like results and you may see something like this. We'll say MEQ per L, like in your plasma or things like that. So this is what it's doing. It's measuring the amount of it, but based on the charge per liter. So a magnesium counts twice as much as, let's say, sodium because it's 2 plus. A calcium counts twice as much as the sodium because it's 2 plus. This stuff, hydrogen phosphate, counts twice as much as a bicarbonate because it has twice the negative charge. So this is not the same as moles per liter, but multiplied by the charge in a sense. So if it was moles per liter, this would be 138 millimoles per liter. This would be 5 millimoles, but this one would have been half of that in millimoles because it's been doubled because of the 2 plus. So that's 4 milliequivalent, but it would have been 2 millimoles because it's doubled because of the charge. So basically you're just multiplying the moles by the charge. So this is 4 milliequivalents, but it's 2 negatives, so it's really 2 moles, but every mole gave me 2 equivalents. So 2 millimoles gave me 4 milliequivalents. So that's how we measure our things. That's all different little ion stuff here. So let's just look at one and try and think about this, if you can make sense out of this. So it's the same as the moles, but you're just multiplying it by the charge. So a Ringer solution, which is a real common thing in hospitals. If you're working on a hospital, I'm sure you probably see like an IV bag, and it even says Ringer solution right on the IV bag a lot of times. So that's a solution sometimes that's used, and it typically has 155 milliequivalents per liter of chloride. Okay? So let's say you gave a patient 1,250 milliliters of that IV solution. How many moles of chloride did you give them? So the doctor orders, so many milliequivalents, so many millimoles, whatever he orders. You figure out, okay, so you're giving 1,250 milliliters. Did you give him enough chloride yet? So let's look at this. Let's try this out here together. So I had 1,250 milliliters of my solution. And I know there's 155 milliequivalents per liter of solution. But I'm not in liters, I'm in milliliters. So first thing I should do is let's turn that milliliter into liter. Now I have liters of solution. Okay. So there's 1,250 milliequivalents per liter of solution. Oh, you're right. Wrong number. Thank you very much. Let's fix it, 155 milliequivalents. So what's the relationship, though, between milliequivalents and millimoles? What's the rate? Every 1 mole of chloride gives how many equivalents of chloride? Just 1, right? Why is that? Because it's just 1 negative, right? If it was 2 negative, I just said 2 equivalents per mole, right? But it's not. So we're in milliequivalents. So let's turn milliequivalents into equivalents. So it's the same thing, milli anything. What's milli? 10 to the what? 10 to the what? -3. Oops, I don't need to erase here. I want to erase this one. Yes, and then you're absolutely right. Every 1 equivalent of chloride is the same as 1 mole of chloride because they're 1 to 1. Because it has that 1 charge right there. Now, if that would have been, like I said, that would have been calcium 2 plus, 1 mole of calcium 2 plus would have been 2 equivalents. 1 mole of aluminum 3 plus would have been 3 equivalents.
Go back to where we got the 1 mole of equivalence times 10 negative 3.
1 milli equivalent is 10 negative 30 equivalents.
Yeah.
Milli anything is 10 negative 3. Just like 1 milliliter is 10 negative 30.
So I understand that part. I just don't understand the equivalence and the milli.
You understand this step?
Yeah.
Because I'm in milli equivalents, but I have to be in equivalence. So how do I convert milli anything to regular 10 negative 30? So just like milliliters to liters, milli equivalents to equivalents. Because the mole is 1 mole per 1 equivalent, not milli equivalents.
Oh, okay, got it.
Okay, so now we cancel out equivalents and we say, okay, so let's figure it up. So how many moles of chloride did you just give that patient? So punch that in your calculators. See what we get. Okay, let's hear some answers. I'm sorry? 0.194. Okay. 0.194 moles of chloride. So that's how much chloride you just gave them. With that much. Okay, well, let's try one where it's not 1 to 1. Let's try like calcium. Calcium 2 plus. So pretty similar. So you take some. Yeah.
What was the answer again?
0.194. Okay, so here's one. You have a little blood work done on the patient. They run it up and they come back with their calcium levels are at 6.4 milli equivalents per liter. You can figure out. Okay, so that's the blood work. Well, how many moles of calcium do they have per liter in 0.5 liters of blood? So think about that. You get 0.50 liters. 6.4 milli equivalents per liter. How many moles of calcium must I have? Okay, well, compare with somebody if you haven't. See what they got, or help them out if they don't know what they're doing. Vice versa.
Oh, is it? it's 2 EQ, but 2 mole.
I think it's in here.
2 EQ per mole.
It's 2 EQ per 1 mole.
So I got that part, but we need to do 6.4.
Yeah, you're right.
Well, or you can do that.
Okay. How many moles of calcium are in a half a liter of this patient's blood? 3.2 times the negative third moles.
No, it's 1.6.
1.6 times the negative third. Okay. Well, let's try it out. See who's right. Try it out. So 0.50 liters. And it tells me there's 6.4 milli equivalents per liter, right? So I'm going to get milli equivalents into equivalents. So turn milli EQ into EQ. So just like any other one, 1 milli is 10 to the negative third. Awesome. And then what's the conversion between equivalents and moles? Which is which? 2 moles per equivalent, 2 equivalents per mole, 2 equivalents per 1 mole. So there's 2 equivalents of charge for every 1 mole of calcium 2 plus. Because again, it's 2 plus, right? So 2 plus. So yeah, divide by 2. And what'd you say it was? Anybody? 1.6 times 10 to the negative third moles of calcium. Great. Sounds about right. And again, like I said, if it would have been, I don't know, phosphate ions, well, that's 3 negative, so you'd have had 3 equivalents per mole, right? It's just multiplying by that charge. Okay. So, now we can also measure quantitatively, well, how much of something does dissolve, how many grams dissolves, things like that. But solubility is based off a few different factors. So when you put that salt, that sugar into water, how much it dissolves is going to be based off a couple of things. First, what are you trying to dissolve it into? What's the solvent? And another thing is, what's the temperature of that solvent? Because you probably know, and generally, if you put, let's say, sugar, try to dissolve it into hot water or cold water, which one is better? Hot water, right? So yes, it's dependent on temperature. So yeah, so temperature has an effect on the solubility of different substances. So the normal way that we measure that, if you want to measure it quantitatively, is grams per 100 milliliter of solvent. So typically it's water, so you say grams of sodium chloride per 100 milliliters of water, or whatever it is. So grams of solute per 100 grams of solvent in typically water. Okay? Now, as far as like a qualitative kind of description, we can talk about a few different things. We can talk about, well, the solution, is it saturated, is it unsaturated? So this is more like a qualitative, not like a numerical thing. We'll talk about a saturated solution. So if you hear somebody say, man, sample is just saturated with salt, or it's saturated with calcium, or it's saturated with whatever it is, sugar, that means they have put in the maximum amount of whatever, sugar or salt, into that solution. And if you put in 1 particle more, it won't dissolve. It'll just fall out on the bottom as a solid. So you've dissolved all you possibly can. So that's called a saturated solution. When you have dissolved all the sugar you can into your coffee, and you've made it as sweet as you can, and you pour in more sugar, it doesn't dissolve, just sits on the bottom as a layer of sugar. So now you've saturated it at that point. You've maximized the amount of unhealthy benefits in your coffee. Way to go. Okay, so that's saturated. Now, any point from 0 up to that point, we say, well, it's unsaturated. So anything less than the max is said to be unsaturated. So you haven't maximized it out yet. You still can add some more sugar, or you can add some more salt, or whatever it is, into that thing. So it'll keep dissolving. So it's unsaturated. If you go on next semester into 102, you've all heard of these things that are like saturated fats and unsaturated fats. Well, it's a similar thing, but in that case, when something is a saturated fat, it's been saturated then in its structure with the most amount of hydrogen atoms possible. So I'll just give you a quick little side note. You don't have to know this, but just for fun. Let's say most fats are carbons and hydrogens and things. So let's say I just had 2 carbons. Well, carbon likes to have 4 bonds. So if I put all the hydrogens I could on here, let's say on these 2 carbons, I've saturated that with hydrogens. That's all the hydrogens I could put on there. But let's say I made it a double bond. So I used up some of the space for hydrogens with carbon-carbon bonds. You see that? So that one is unsaturated. The same thing in fats you'll see as you go on. So unsaturated fats tend to have double bonds, triple bonds, things like that, because they don't have the maximum amount of hydrogens. Well, same thing in this case. A saturated solution has the maximum amount of whatever the solute is dissolved. Okay. And then there's a third one that sounds kind of odd, because I just told you the max is called saturated. Well, you can actually kind of like finagle that. And you can trick solutions to actually going above their normal max, which makes it not really a max, but it's the normal max at that temperature. And you can do something called super saturated, and they're really kind of cool solutions. We'll try to set one up for you in lab. It's this week or next week. We'll see if we can get it to do it in lab. I have a video though to show you here in a second. But basically, what you do is you trick the compound into dissolving more solid than it normally would at that temperature. And I'll show you how we do that on the next slide here. So the normal max at the temperature is saturated. Less than that's unsaturated. But again, you can kind of trick it sometimes into being super saturated. Okay, so how does that happen? Let's look here and I'll show you. So, generally, as you all just told me, solids tend to be more soluble as you increase the temperature, right? You all just told me that you get more sugar in a hot coffee or hot water than you can cold coffee, right? Or more salt or more Kool-Aid or whatever dissolves into hot versus cold. That is very true. So here is a graph of a bunch of solids and their solubility on the y-axis versus the temperature on the x-axis. So you see, as temperature goes up, you can dissolve more and more and more and more of every solid pretty much as they get more soluble. Right? Now, it varies depending on how much more, but it pretty much goes up for all of them, right? Just more or less. Are you with me? So how do I make a super saturated solution? Well, certain ions, what you can do is, let's say room temperature was here and it was at 20 degrees Celsius, okay? And let's say I want to dissolve, KClO3, potassium chlorate. Well, at 20 degrees, I can normally put about 7 grams in 100 grams of water. You see that? Are you with me? Well, let's say I heat it up to 50 degrees Celsius. Well, now I can put in about 18 grams. So what you do, basically, you have your solution, and you warm it up, and you put in 18 grams or 12 grams or whatever. And then when you cool it back down, if you don't touch it or stir it or anything, you kind of like trick it. It goes back down to here, and it really only wants 7, but you snuck in an extra 2, 3, 4, 5 grams at a higher temperature, and it kind of stays there. But it's super unstable. And if you just like look at it sideways or sneeze on it, all of that extra 3, 4, 5 just boom falls out in a second like an avalanche. You'll see. So that's called a super saturated solution. Now the one ionic compound that's most famous for doing this is this stuff. Can you name that? Sodium acetate. Yeah, exactly. So sodium acetate is very famous for doing this, where you can take a solution. Let's say you heat it up here then at 55 degrees, and you put in 100 grams roughly. And then you cool it off down to like 20 degrees. Well, at 20 degrees, the max is supposed to be, what is that? Like 82. So I've snuck in an extra 18 grams. Are you with me? Okay. But those 18 grams don't really want to be there. So if you give like I said, a little nudge of any kind, that extra 18 grams will just fall out in a heartbeat. So that's kind of how you make a supersaturated solution. So let me just show you. So here's a little picture of it, but I'll show you a couple of videos I have that I think are kind of nifty. See if I can get these videos to work. Go back. Did it click it? I don't think it did. Did it click it? Oh, now we're doing something. There it goes. Whatever. Who cares? Load my video here. Oh, I should plug in my audio then real quick. Of course, I should have had this loaded. It's going to take a while now, apparently. Do I have any audio? Allow hearing loss. Can you kind of hear that?
A small crystal of sodium acetate will be added to the solution.
So real quick, so what's happened here is they've done that. Had the solution, warmed it up, dissolved a whole bunch, and now they cooled it back down. Now they take a super teeny tiny little crystal and just drop that in, like I said. And this little tiny crystal is enough just to start an avalanche effect and knock out the extra 5, 10, 20 grams that are in there. I mean, look, it's like a little speck of dust. They drop it in there. That little amount of a little disturbance is enough to knock out the extra. Just like an avalanche. Kaboom! It all just falls out, all the extra. Isn't that awesome? Because that was all there in solution, but it didn't really want to be there. You kind of tricked it to be in there. And it all just falls out.
Here is the process again in slow motion.
I mean, that's making a solid. I mean, it is making a solid, yeah.
So can you do that with sugar and coffee?
I don't think sugar really is quite. Okay, back up. Most solids don't do this. Like I said, most solids, what happen is it's hot. You put in extra. You put in extra whatever is salt or sugar. Let's say then. Don't do that, and you cool it off. Please stop. And you cool it off. Okay. What was it? Okay. So most solids, what happens? Let's say sugar and coffee. If you heat it up and you cool it off, as it cools off, all the extra falls out as you cool it off. It kind of falls out and falls out and falls out. Except for sodium acetate, for whatever reason, sodium acetate will stay in there until you flick it or nudge it or whatever. So I have one more other little video that I want to show you that's like this one. I think is really cool. You can really see the crystals form in this one.
So not all solutions can be supersaturated.
Yes, not everything can be supersaturated, at least not easily. So watch this one. This one you can really see like the crystals kind of form like needles. And when they hit the bottom, then they like change directions and grow back up. Can you see them growing back up now from the bottom? So they grow to the bottom, kind of stalactites at the bottom, kind of go like stalagmites, grow back up. Isn't that cool? Nuts, huh? So yeah, so that's called supersaturated. So again, so you tricked it, and you put a little extra in there, more than it wanted to have, and then you just knock it out. So that's called a supersaturated.
So we're going to play a little game today.
No, we're not.
Guess how many packing peanuts you can fit inside this tiny little...
Shut up. Okay. Now with gases are just the opposite. Gases are more soluble as you lower the temperature. And you all know this because you probably know that a cold soft drink is always fizzier than a warm soft drink, right? Because again, that's why. Because you actually dissolve more gases into a cold solution than you can into a warm solution. So they're just the opposite of solids. So solids, as you warm them up, you get more dissolved. Gases, as you warm them up, less dissolves, and it begins to come out. So you see here like the cold Coke and the warm Coke, right? So the cold one, the warm one, all the extra starts to come out because it's too warm. So it won't dissolve, it won't stay soluble. Okay, so there is a way that you can actually measure this if you want. It's called Henry's Law. This measures this, and it basically says with Henry's Law that the higher the pressure of the gas is above the liquid, the greater the solubility of the gas will be in the liquid. So, when you open up a can or a bottle of Coke or a Mountain Dew or whatever, what do you always hear when you open it? A little psst, right here, that little sound, right? Okay, so they are using Henry's Law. What they are doing in their can or in that bottle is they are adding in a very high pressure of the gas, in this case carbon dioxide, above the liquid. And when they put in all that extra gas above it, it forces more of that gas to go into the liquid and to actually dissolve, and it keeps it nice and fizzy. So let me just draw a little picture here for you. I know you love my wonderful artwork. So let's say I have a bottle here. Here's my lovely bottle. This is a 2-liter bottle, let's say. Okay, so I have in here my Cokes. I'll find a brown color. Here's my brown. So I have in here, sugar and carbon dioxide and phosphoric acid and lots of nasty things throughout your teeth. And, so what do? Well, I'm going to put extra carbon dioxide above it. So I'm going to put in extra gas up here. So what I want to do is I want to increase the pressure, because from the last chapter then, if you add in more molecules, that's going to increase the pressure, right? So more gas, more collisions, increases the pressure. So you're just naturally going to have just a few molecules we learned escaping naturally, right, into the gas phase. And that's called the vapor pressure. What I'm going to do is I'm going to juice it. I'm going to add in extra carbon dioxide. As that extra gas is bouncing around up here off the walls and stuff, some of it's going to bounce into the solution. So you're going to force some of this into dissolve. So that's basically Henry's Law. If I increase the pressure of the gas up here above it, then I'm going to force more of that gas into the liquid, and I'm going to increase the solubility of that gas into the liquid. So again, it's like I said, in the Coke bottle, you'll hear that psst, that hit, because they've done that. So they have their Coke bottle, and the last thing they do is they force in a whole bunch of carbon dioxide and they seal it off. And all the carbon dioxide stays up here, and it keeps bouncing and bouncing, and keeps on colliding into the Coke and dissolving, and it keeps it fizzy. Right when it's done that. But once you open it, all that pressure is gone, and now it begins to want to leave, and it gets flatter and flatter as it stays open, right? Because you kind of like force extra in there with the pressure. But once the pressure is gone, that extra begins to naturally leave, and it gets flatter the longer it sits out, right? So that's Henry's Law. Okay. Awesome. Exciting. Okay, so let's look at some solubility here. How can I predict when things are going to be soluble or not? So ionic compounds that do dissolve, we call those soluble salts. And remember again, salt is just a fancy word for an ionic compound. Salt is not necessarily NaCl. Salt is just any kind of a ionic compound. So if it does dissolve, we say it's soluble. If it doesn't dissolve, we say it's insoluble. Pretty straightforward, I think. And the cool thing is we were going to see some of this as we begin to mix different salts together. We'll kind of learn, okay, which ones stay soluble, but which ones don't. Which ones make solids and they fall out and make orange and yellow and black and green and different colors here. So these floaty things, these are the insoluble salts because they're not dissolving out. They're staying as chunks. And you saw some of this in the library a couple of weeks ago where you mix some chemicals and you make a solid come out, right? So it was like soluble, mix them, boom, suddenly it's insoluble and you make a solid come out. So, by the end of this chapter, you'll be able to predict which ones are going to mix and make solids, which ones won't make solids. Kind of cool. So here are some solubility rules you need to put in your brain. So make a note, table 8.8. Table 8.8. They're pretty straightforward. I'll show you how they work. It's not as bad as it looks. So just make a note, table 8.8. So, if you have an ionic compound, if it has any one of the group 1 elements in it, like, remember, lithium, sodium, potassium, any of those, anything with that is always soluble. So lithium anything. Lithium chloride, lithium fluoride, lithium bromide, lithium carbonate, lithium whatever you can think of. Sodium anything, potassium anything. Those will always dissolve in water. So anything with lithium, sodium, potassium, again, all those ones in that group 1A, always soluble. No exceptions that we know of. Anything that has ammonium, always soluble. No exceptions. Anything that has nitrate or acetate, those always dissolve in water. No exceptions. So anything nitrate you can think of. It could be sodium nitrate, but it could be iron 3 nitrate, uranium 6 nitrate, lead 2 nitrate, anything nitrate, anything acetate. Those all dissolve in water, no exceptions, okay? So any of the group 1As, like lithium, sodium, potassium, anything with ammonium, anything with nitrate or acetate, those all dissolve in water. You can just bet your bottom dollar on it, okay? Those all dissolve. Awesome. Anything with chloride, bromide, or iodide, those all dissolve except for 3 exceptions. Silver, lead 2, and Hg2 2+. Those are the 3 exceptions. But anything else with chloride, any other metal you can think of, any other of the 70, 80 metals will all dissolve with chloride or with bromide or iodide, except silver, lead 2, this is called mercury 1 technically. Okay? And the last rule, anything with sulfate, they're all soluble too. All the sulfates are soluble except barium, lead 2, calcium, and strontium. Okay? So you just for now just ignore this for right now, but just pretty much everything else is going to be insoluble. So any combination you can think of that doesn't have lithium or sodium or potassium or ammonium or nitrate or acetate or these in it, like if it has a carbonate, has a sulfide, it has, I don't know, whatever else you learned, phosphates, hydroxides, everything else pretty much is going to be a brick. It's going to fall out as a solid. It's going to be insoluble. Unless it's partnered with ammonium or sodium. Do you kind of see what I'm saying? So pull out your handout. Let's work on the handout and I'll show you how it works. But I think I even have the chart on your handout. Have the solubility rules on your handout? They're not on there on the last page. I think I put them on there somewhere. I lied, I guess. I thought I put them on there. Okay, so let's just look here, and this will make sense for us. So, determine if each of these is soluble, means it dissolves, or insoluble, just makes a solid, just falls to the bottom. Potassium hydroxide. So, will that dissolve in water, or will it just fall to the bottom as a white solid? Why do you know that will dissolve in water? Because it has potassium. And anything that has potassium is soluble all the time, no exceptions. So, why? Has potassium, so make a little note, right? Potassium, right? Right, potassium, anything, always soluble. Okay? How about the combination of silver and bromide? If I put that in the water, will that dissolve or will that just fall out as a white precipitate. Okay, why? Yeah, all bromides are soluble, except silver is one of the three exceptions that when it partners with bromide, doesn't dissolve. So silver bromide, lead 2 bromide, and this mercury bromide. Every other bromide would though. Potassium bromide, lithium bromide, iron bromide, whatever bromide you can think of. Nickel, chromium, molybdenum, whatever. They all would, but silver is one of the only ones that won't. Okay? Good. Calcium chloride. Okay. Nicole's shaking her head, yes. Why? Tell me why. Because chlorides are all soluble except silver, lead, and mercury, and calcium is not one of those, so calcium chloride, yes, it would be soluble. So calcium chloride, you would predict, would dissolve into water, right? Okay, your turn. Try the next two. Make a prediction. Lead, whatever that is, I don't want to tell you lead something. Lead 2, lead 4, what is that? And lead something, whatever that other thing is, figure it out. Okay, so discuss with your neighbor D and E. What do you think? Soluble or insoluble? Soluble or insoluble? Talk it over. Okay, so name D for me. Name it for me.
Lead.
Name it. What's it called? Lead.
Lead 2.
Lead 2 nitrate. So is that soluble?
Yeah.
How do you know? Nitrate. Anything that has nitrate. Doesn't matter. Always soluble. Name E for me.
Lead 2 sulfate.
Lead sulfate.
It's definitely lead something. Is it lead 2?
That one.
Is it 1, 2, or 4? I heard all of those. What's the charge on sulfate? 2 negative. So it's lead. Yeah, it is lead. It is lead 2 sulfate. So, what's the rule for sulfates? They're all soluble, except with lead 2 is an exception. Now notice, only lead 2 is an exception. Not all leads. That's why you got to know what it is. Lead 2. If it was lead 4, let's say, it would have been soluble. I'll give an example. Let's say it was lead 4. Let's say it was PbSO4 2. That's lead 4. That would have been soluble. Because only lead 2 is the exception, okay? So that's where so that's the only little tricky thing. Lead 2 is the exception, right? Not any lead, just lead 2. Okay. Okay, well this is really important when you think about this, knowing when things are going to be soluble, because I've heard horror stories like in hospitals where they will take 2 medicines and they are both nice and liquids, and then they mix them in a patient's bloodstream, and they wind up combining a sulfate with, let's say, a barium, and it makes a solid in their arteries, clogs it, and kills them. So you have to know solubility rules, so you make sure that when you're mixing things, you're not getting a combination that's going to be insoluble, and things like that, right? So solubility, an important thing to think about, right? So, okay. So let's do what I mentioned here. We only got a couple of minutes left, unfortunately. Time flies when you're having fun. We're going to discuss these double replacement reactions. Remember I mentioned we have 2 things changing products, changing partners. We're going to actually predict now what are the products. So I really feel like finally in Chapter 8 we're going to feel like real chemists. You're going to be able to actually write a reaction and actually then predict what the products are going to be. So when I mix A and B, I'm going to know what I'm going to get out. So it's kind of fun. So it really is like you're doing a square dance and you're changing partners here. So you're just going to take each of the ionic compounds and you're going to give them new partners. So you see that here. I have cation A and anion X. Cation B, anion Z. I just take the anions and change them. Just give them new partners. And that's how it works. I give them new partners. So A goes with Z and B goes with X. So that's called, remember, a double displacement or double replacement. You just change the two partners. Okay? So let me show you. Got 3 minutes here. Now, remember, the reactions can make liquids, solids, gases, aqueous, any of these different states. And now that we know the solubility rules, we can begin to predict, oh, is that one going to be aqueous or that one's going to be solid? Because you know your solubility rules. So again, if it's soluble, based on your rules, you're going to put AQ. If it's insoluble, you're going to put S. So we can use those solubility rules to actually begin to predict, oh, it's going to make a solid, or it's going to make an aqueous, or whatever. And then we'll see here in a little bit how to predict the other ones, liquids and gases. Okay, 2 minutes. Okay. Well, but if everything is aqueous, let's say they mix together and combine. So you have A and X is dissolved up, and B and Z is dissolved up, and you get out AZ and BX, and they're still dissolved. Nothing happened. You just had a bunch of ions swimming around, and they're still swimming around. Nothing combined to make a solid or a liquid or a gas. In that case, literally it's no reaction. So you have to have either a solid being made, a liquid being made, or a gas being made for there to actually be a reaction. Else you're just basically mixing chemicals. So if everything is aqueous, then there was no reaction. That's the easiest way I know to say it. If all the reactants and products are still aqueous, then you just dissolved a bunch of ions and they just swirled around, nothing combined to make anything. Okay, so let's show you one and we'll wrap this up in our last minute here. So let's say I have silver nitrate and potassium chloride. Well, we're going to just find him a new partner. So this cation is with this anion, this cation with this anion. We're just going to swap them. So silver was with nitrate, potassium was with chloride. We're going to swap them. I'm going to put silver with chloride and potassium now with nitrate. But you have to do this still, just like any kind of ionic compound, you base it on charge. So you can't just automatically say, oh, it's one silver here, it's one chloride here, it must be 1 and 1. We get based off the charges. What's the charge on silver? What's the charge on chloride? Then you figure out what silver chloride is. So it's kind of your naming thing. What's the charge on potassium? What's the charge on nitrate? Figure it out and make a neutral compound. Now in our case, silver is 1 plus, chloride is 1 negative, so silver chloride would be AgCl. And potassium is 1 plus, nitrate's 1 negative, so potassium nitrate would be KNO3. Right, so you just swapped them. You see that, how you just swapped them? We just a little do-si-do square dance there. Swapped them out. Now our last thing, we're out of time, is use our solubility rules. Silver chloride, aqueous or solid? Aqueous meaning soluble, or is it solid meaning insoluble? Makes a solid because chlorides are all soluble except with silver. So that would make a solid, so you write parenthesis S. How about this one, potassium and nitrate? All potassium soluble, no exceptions. All nitrate soluble, no exceptions, so aqueous. Okay, well, I'll upload that here in a second, and we will